Let knowledge flow like a river, without any hindrance. Don't make it like a stagnant pool. Hello, everyone. I'm PS Chaturji, and a warm welcome back to today's DIY Excel project. You are watching Structural Design Only, a channel with a different vision. Before we dive in, a quick note for my non-civil engineer viewers. While we'll be tackling some technical concepts today, please feel free to follow along. Simply treat the engineering terms as numbers, and focus on applying the Excel process to your own DIY spreadsheet projects. Today's video is titled, Design of Short Column, IS 456, 2000. No charts needed. Explained in Excel. This is an PowerPoint and Excel presentation and a perfect DIY project, especially for my fellow civil engineers. In this episode, we're going to dive into several critical aspects of a short, fixed-end column, without using the charts from SP-16 in Excel. First, we will review the theories for the design in a PowerPoint presentation. Then, for numerical analysis, as usual, we will use our Excel spreadsheet. If you're new to the channel, I highly recommend checking out how to design our CC column in Excel. It will be incredibly helpful. I published that video on July 5, 2022, and for this Excel-based calculation sheet, I used the charts from SP-16. Now, let's move to our next slide, for the methodology of the design on PowerPoint. Title of this slide is, Know Your Column Section and Design Parameters. On the left side of the screen, you will find the cross-section of a short and tied column, on the XZ plane. And on the right-hand side, you will find the design parameters and dimensions of the column. Let's begin with the design parameters. Point number 01, Characteristic Strength of Concrete, or Grade of Concrete. This is denoted by the capital letter M. As per IS 456 2000, this value should not be less than 25 Newton per square millimeter. Point number 02, Grade of Steel, or Characteristic Strength of the Steel Rebar. It is denoted by Fy. According to IS 456, this value should not be less than 415 Newton per square millimeter. Now, looking at the cross-section of the short and tied column on the right-hand side of the screen. Point number 03, Overall dimension of the column in the X direction is denoted by the capital letter D. Point number 04, Overall dimension of the column in the Z direction is denoted by the small letter b. As per clause 26.4.2.1 of IS 456 2000, the least lateral dimension of a square or rectangular RCC column should not be less than 200 mm. That means, the dimension D or B should not be less than 200 mm. In practice, we generally use 250 mm as the minimum lateral dimension. Point number 05, Clear cover. This is the perpendicular distance between the extreme edge of the column and the external surface of the rebar, in both X and Z directions. It is denoted as CO. As per clause 26.4.2.1 of IS 456:2000, The nominal cover for columns shall not be less than 40 mm, or not less than the diameter of the bar, whichever is greater. However, for columns with minimum dimension of 200 mm or less, and using bars up to 12 mm diameter, this cover may be reduced to 25 mm. In practice, we generally adopt 40 mm as the clear cover. Point number 06. Diameter of the provided bars is denoted by dB. The preferred minimum bar diameter is 12 mm. Point number 07. Effective cover. We denoted the effective cover as d bar prime. Its value is equal to the clear cover, minus half of the bar diameter. Point number 08. Effective dimension of the column in the x direction. This is denoted as DEFF. Its value is equal to capital letter D, minus d bar prime. Point number 09. Effective dimension of the column in the z direction. This is denoted as BEFF. Its value is equal to small letter b, minus d bar prime. Point number 10. Number of bars used in the design is denoted by the capital letter N. Now, let's move to the next slide for more details. Title of this slide is, Know Your Short and Tied Column. Let's start with the basics of designing a short and tied column. On the left side of the screen, you'll see an illustrative diagram of a short and tied column. I'll walk you through each key part of it. First, what exactly is a short and tied column? A column earns this title when it follows these specific criteria. For the first point, both ends of the column along the x and z axes must be tied to the beams. This means the column's rotation at its ends is fully restricted. Next, the overall height of the column is denoted by the capital letter H. We measure it from the bottom of the bottom beam to the top of the top beam. The unsupported height of the column is denoted by H unsup. This is the clear distance between the floors, measured from the top of the bottom floor to the bottom of the top floor. Point 4. Finally, the slenderness ratio is the unsupported height, H unsup, divided by the column's least dimension, either its depth d or width b. For a column to be considered short, this ratio must not be greater than 12. Now, let's move to the next slide for more details. In this slide, you are seeing an impression of the actual Excel spreadsheet. At first glance, most of the cells appear blank. In reality, they are not empty, the figures are simply hidden. Only the parameter titles and result headings are visible. Since a clear and structured demonstration is difficult to achieve directly in Excel, I am presenting the process here in PowerPoint, as suggested by ChatGPT. This is the starting point of column design. Cells B2 to B6 are drop-down menus for selecting design inputs such as concrete grade, steel grade, clear cover, number of bars, and bar diameter. Cells B7 to B9 take direct input values. These are column depth, column width, and unsupported length. Now, notice cell C9. It automatically checks the slenderness ratio. Here it shows long column, and in cell D9 we see not applicable. Why is that? The least lateral dimension of the column, that is, column width in Z direction, is 200 mm. The unsupported length is 3.0 meter, or 3000 mm. The ratio, unsupported length divided by column width in Z direction, therefore equals 15. Since this ratio is greater than 12, the column is classified as a long column. However, this application is valid only for short columns. That is why all the other cells remain blank. Finally, by using define name, I have assigned the name check1 to cell D9, as this represents the first check in our design process. Now the question is, how can we hide the figures in the cells? For example, consider cell D2. Here we find the value of effective cover. The assigned name of the cell is C_EFF. We know that C_EFF equals to CC plus B_D divided by 2. Where CC and B_D are the assigned names of the clear cover and the maximum diameter of the bars respectively. To hide this formula result when our column is a long column, we use another formula as a condition before it. The final formula becomes, equals to, if check1 equals to OK, then CO plus B_D divided by 2, blank quotation. The simple meaning of this formula is, if Excel finds check1 equals OK, then it will calculate CO plus B_D divided by 2. Otherwise, it will keep the cell blank. In cell D3, we find the value of effective width. The assigned name of the cell is B_EFF. We know that B_EFF equals to B minus C_EFF. Here B is the assigned name of the overall width. To hide this formula result when our column is a long column, we apply a condition before it. The final formula becomes, equals to, if check1 equals to OK, then B minus CEFF, blank quotation. The simple meaning of this formula is, if Excel finds check1 equals OK, then it will calculate B minus CEFF. Otherwise, it will keep the cell blank. In cell D4, we find the value of effective depth. The assigned name of the cell is D_EFF. We know that D_EFF equals to D minus C_EFF. Here D is the assigned name of the overall depth. To hide this formula result, we apply a condition before it. The final formula becomes, equals to, if check1 equals to OK, then D minus CEFF, blank quotation. The simple meaning of this formula is, if Excel finds check1 equals OK, then it will calculate D minus CEFF. Otherwise, it will keep the cell blank. In cell D5, we find the value of gross area of the concrete. The assigned name of the cell is AC_gross. We know that AC_gross equals D multiplied by B. Once again, to hide this formula result, we apply the same condition before it. The final formula becomes, equals to, if check1 equals OK, D multiplied by B, blank quotation. I think, you already know the simple meaning of this formula. In cell D6, we find the value of net area of the concrete. The assigned name of the cell is AC_net. We know that AC_net equals to AC_gross minus A_SC. Here, A_SC is the area of steel provided for the design. The final formula becomes, equals to, if check1 equals to OK, AC underscore gross minus A underscore SC, blank quotation. In cell D7, we calculate the area of steel. We already know, the assigned name of the cell is A underscore SC. We know that A underscore SC equals to N multiplied by pi, divided by 4 multiplied by B underscore D, squared, and B underscore D is the assigned name of diameter of the bars. Here, N is the number of bars, and bar diameter in millimeters. The final conditional formula becomes, equals to, if check 1 equals to OK, N, multiplied by pi, divided by 4, multiplied by B underscore D, squared, blank quotation. In cell D8, we calculate the percentage of steel. The assigned name of the cell is small letter p. We know that p equals to A underscore SC divided by AC underscore gross, multiplied by 100. Here, A underscore SC is the area of steel provided, and AC underscore gross is the gross area of concrete. Unit of P is percent. The final conditional formula becomes, equals to, if check 1 equals to, OK, then A underscore SC divided by AC underscore gross multiplied by 100, blank quotation. We are hiding the results, to avoid the confusion that will occur when Excel finds the column as a long column. In the next slide, we will see how to select the load case for our design. This is sheet 2, impression of the same Excel sheet, for selection of the governing load case. In this sheet, there are 2 tables. For the moment, table 2 is hidden. We will focus only on table 1, and the table is loads and checking column capacity 01. In column B, we see the load case numbers. In column C, we see the factored axial load. It is written as FY. But for design, we will call it PU. In column D and column E, we see the factored moments. These are moments about the x-axis and the z-axis. We will call them MUX and MUZ. All loads shown here are ultimate loads. For the design, we need to select the governing load case. The question is, how do we decide this? First, select cell A4. It is under the heading Load plus Absolute Moments. Now type this formula, equals to if, check underscore 1 is greater than, less than, blank quotation. C4, plus ABSD4, plus ABSE4. The meaning is simple. If check 1 is not OK, the cell remains blank. Otherwise, it will calculate the sum. The sum is PU, plus absolute MUX, plus absolute MUZ. This is for load case 201. Now, copy the formula from cell A4. Paste by selecting the option Paste Formula, it down to cells A5 through A16. Because check 1 is not OK, all cells in column A remain blank. Now we have to prepare the column with the heading check. First, select the cell F4. In this cell, type this formula. Equals to, if, check underscore 1, not equal to, OK, then, blank. Otherwise, if, and, PUY underscore cap, greater than or equal to, C4, and, MUX underscore 1, greater than or equal to, absolute value of D4, and, MUZ_1, greater than or equal to, absolute value of E4, then, OK, otherwise, check. The simple meaning of this formula is, if, check_1, is not equal to OK, then the cell will remain blank. Otherwise, if, the axial load capacity, is greater than or equal to the applied vertical load, and the moment capacity about X, is greater than or equal to the applied moment about X, and the moment capacity about Z, is greater than or equal to the applied moment about Z, then the cell will display OK. If any of these conditions are not satisfied, then the cell will display check. As a recommendation for the adjustment in the overall design. Here, PUY_cap, is the axial load capacity of the column. MUX_1, and MUZ_1, are the uniaxial moment capacities of the column. I will discuss these, in the next portion of the video. Now, copy the formula from cell F4. Then, paste by selecting the option, Special Paste, Formula. Do this down to cells F5 through F16. Because check_1, is not equal to OK. All the cells in column F, remain blank at this stage. Now, the only remaining task for this table is providing a conditional formatting, so that we can easily visualize the row for the selected load case and its loads. Now the question is, how can we do this? First, select the cells A4 to E4. Then, open the conditional formatting menu. From this menu, select the option Use a formula to determine which cells to format. In the dialog box, type this formula. Equals to, $A4, equals to, max, $A$4, colon, $A$16. The simple meaning of this formula is, if the value in cell A4 is equal to the maximum value from the range A4 to A16, then the condition is true. Otherwise, it is false. Next, click Format. Go to the Fill tab. Choose a green fill color. The meaning is simple. If the value of A4 is equal to the maximum value in the range A4 to A16, then the entire fourth row will turn green. Otherwise, nothing will change. To apply the same formatting to the whole table, do this. Select the cells A4 to E4. Click Format Painter. Then drag it down from A4 to E16. Now the conditional formatting is complete. Since all the cells are blank at this stage, no changes will be visible. Next, I am going to demonstrate the preparation of the second hidden table in this sheet 2, with the title, Selected Load Case and Loads, 02. Now, we will unhide the table Selected Load Case and Loads, 02 of this sheet. And now we are seeing both the tables together. In Table 2, there are 4 columns, from H to K. In cell H3, we are going to display the selected load case. In cell I3, we are going to display the selected ultimate axial load, PU. And in cells J3 and K3, we are going to display the selected MUX and MUZ. We already know that these are the ultimate moments about the X and Z axes respectively. Now the question is, how can we do this? It is very simple. We will use the VLOOKUP formula for that. First, for the load case, the formula is equals to, if, check_1, not equal to, OK, then blank. Otherwise, VLOOKUP, open bracket, max, $A$4, colon, $A$16, comma, $A$4, colon, $E$16, comma, 2, comma, 0, close bracket. The simple meaning of this formula is, if check_1 is not equal to OK, then the cell will remain blank. Otherwise, VLOOKUP will find the value of the selected load case. Here, the value of max, $A$4 to $A$16, is the lookup value. The range $A$4 to $E$16 is the table array. 2 is the column index number. And 0 means exact match. Formula for selecting maximum PU is equals to, if, check_1, not equal to, OK, then blank. Otherwise, VLOOKUP, open bracket, max, $A$4, colon, $A$16, comma, $A$4, colon, $E$16, comma, 3, comma, 0, close bracket. The structure of this formula is the same as the previous one. The only difference is the column index number. Here it is 3, instead of 2. Formula for selecting maximum MUX is equals to, if, check_1, not equal to, OK, then blank. Otherwise, VLOOKUP, open bracket, max, $A$4, colon, $A$16, comma, $A$4, colon, $E$16, comma, 4, comma, 0, close bracket. The structure is the same as before. The only difference is that the column index number here is 4, instead of 2 or 3. Formula for selecting maximum MUZ is equals to, if, check_1, not equal to, OK, then blank. Otherwise, VLOOKUP, open bracket, max, $A$4, colon, $A$16, comma, $A$4, colon, $E$16, comma, 5, comma, 0, close bracket. Again, the structure is the same as before. The only difference is that the column index number here is 5, instead of 2, 3, or 4. Since check_1 is not equal to OK, we are seeing all the cells in this table are blank at this stage. Now, I am returning, for the remaining parts of sheet 1. Now, we are inside sheet number 1 of column design without charts, SP-16. Our next step is simple, we'll bring the elected load values from sheet number 2 to sheet number 1. In cell F3, we type equals PU_elected. In cell F4, equals MX_elected. And in cell F5, equals MZ_elected. PU_elected, MX_elected, and MZ_elected are the assigned names of PU, MUX, and MUZ in sheet 2. Now, let's look at the formula for the contribution of concrete in load capacity. In cell F7, we type equals if open bracket check underscore 1 equals OK, comma 0.4 multiplied by FCK multiplied by AC underscore NT divided by 1000, comma double quotes close bracket. That means if check underscore 1 is OK, Excel calculates 0.4 times FCK times ACNT divided by 1000. Otherwise, it leaves the cell blank. Next, let's see the contribution of steel in load capacity. In cell F8, we type equals if open bracket check underscore 1 equals OK, comma 0.67 multiplied by Fy multiplied by ASC divided by 1000, comma double quotes close bracket. This means if check underscore 1 is OK, Excel calculates 0.67 times Fy times ASC divided by 1000. Otherwise, the cell remains blank. Finally, let's calculate the total capacity of the column. In cell F9, we type equals if open bracket check underscore 1 equals OK, comma sum open bracket F7 colon F8 close bracket, comma double quotes close bracket. So, if check underscore 1 is OK, Excel will add the values of F7 and F8. Otherwise, it will keep the cell blank. Now, we are going to see the formulas for step 2. First, the uniaxial moment capacity around the x-axis. The defined name of the cell is mu underscore x1. The formula for cell B12 is equals if open bracket check underscore 1 not equal to OK, comma double quotes for blank, comma open bracket 0.15 times FCK times B times D underscore effective squared close bracket divided by 10 to the power 6 close bracket. In simple words, if Excel finds that check underscore 1 is not equal to OK, cell B12 will stay blank. Otherwise, it will display the value of mu underscore x1 from this formula. Next, in cell D12, we type the formula for uniaxial moment capacity around the z-axis. The defined name of the cell is mu underscore z1. The formula is equals if open bracket check underscore 1 not equal to OK, comma double quotes for blank, comma open bracket 0.15 times FCK times D times B underscore effective squared close bracket divided by 10 to the power 6 close bracket. In simple words, if Excel finds that check underscore 1 is not equal to OK, cell D12 will stay blank. Otherwise, it will display the value of mu underscore z1 from this formula. Finally, in cell F12, we type the formula for axial load capacity along y-axis. The defined name of the cell is pu underscore y cap. The formula is equals if open bracket check underscore 1 equals OK, comma double quotes for blank, comma open bracket 0.40 times FCK times AC gross plus 0.67 times Fy, times ASC, close bracket, divided by 1000, close bracket. In simple words, if Excel finds that check_1 is not equal to OK, cell F12 will stay blank. Otherwise, it will display the value of PUY cap from this formula. Cell F11 is our check2, and the defined name of the cell is check_2. When Excel finds that PU_Y cap is greater than PU, it will display OK. The formula for cell F11 is, equals, if, open bracket, check_1 not equal to OK, comma, double quotes for blank, comma, if, open bracket, and, open bracket, check_1 equals OK, comma, PU_Y cap, less than PU, close bracket, comma, check, comma, OK, close all brackets. In simple words, if Excel finds that check_1 is not equal to OK, then cell F11 will remain blank. If Excel finds that check_1 equals OK and PU_Y cap is less than PU, it will display check. Otherwise, it will display OK. Now we move to cell B14, which has the defined name PUZ. This is the axial load capacity, sometimes called the theoretical crushing capacity of the column. The formula here is, if check1 is not equal to OK, the cell will stay blank. Otherwise, it calculates 0.45 times FCK times the gross concrete area, plus 0.75 times Fy times the steel area, all divided by 1000. That gives us the ultimate axial load carrying capacity, PUZ. Next is cell D14, defined as MUX over MUX1. This shows the ratio of applied moment about the x-axis to the uniaxial moment capacity about x. The formula says, if check1 is not OK, the cell remains blank. Otherwise, it takes the absolute value of MUX, divides it by MUX1, and rounds the result to 1 decimal place. So, cell D14 directly shows how much of the x-axis moment capacity is being used. Finally, cell F14, defined as MUZ over MUZ1. This is the ratio of the applied moment about the z-axis to the uniaxial moment capacity about z. Again, the formula is the same structure. If check1 is not OK, the cell stays blank. Otherwise, it takes the absolute value of MUZ, divides it by MUZ1, and rounds to 1 decimal place. So this cell tells us how much of the z-axis moment capacity is being used. On cell B15, we are going to calculate the value of ratio of PU and PUZ. Defined name of the cell is PU_PUZ. This is the ratio of ultimate axial load in y-axis PU, and axial load capacity PUZ. Again, in the formula structure, first portion is same as usual. If check1 is not OK, the cell stays blank. Otherwise, it takes the value of PU, divides it by PUZ, and rounds to 1 decimal place. So this cell tells us how much of the y-axis load capacity is being used. For finding the interaction ratio, we first need the value of alpha n. As per clause 39.6, on page 71 of IS 456, 2000, the value of alpha n depends on the ratio of Pu to Puz. If Pu over Puz is less than or equal to 0.2, then alpha n is taken as 1. If Pu over Puz is greater than or equal to 0.8, then alpha n is taken as 2. For values in between, alpha n is calculated by simple linear interpolation. Now, on cell D15, we are going to calculate the value of alpha n. Defined name of the cell is small letter an. Formula is equals to if open bracket check 1 not equals to OK, comma blank quotation, comma if open bracket Pu underscore Puz less than or equals to 0.2, comma 1, comma if open bracket Pu underscore Puz greater than or equals to 0.8, comma 2, comma 1 plus open bracket Pu underscore Puz minus 0.2 divided by 0.6. Close all brackets. Simple meaning of the formula. Again, in the formula structure, first portion is same as usual. If check 1 is not OK, the cell stays blank. Second portion, if Pu underscore Puz is less than or equals to 0.2, then value of alpha n equals to 1. Third portion, if Pu underscore Puz is greater than or equals to 0.8, then value of alpha n equals to 2. Fourth portion, if Pu underscore Puz is in between 0.2 and 0.8, then interpolated value of alpha n equals to 1 plus Pu underscore Puz minus 0.2 divided by 0.6. On cell E15, we are going to calculate the value of interaction ratio. Defined name of the cell is interaction. Formula for interaction ratio is equals to if open bracket check 1 not equals to OK, comma blank quotation, comma open bracket mux underscore mux1 to the power an close bracket plus open bracket muz underscore muz1 to the power an close bracket. Simple meaning of the formula. Again, in the formula structure, first portion is same as usual. If check 1 is not OK, the cell stays blank. In second portion, it will calculate the value of the interaction ratio by using the formula mux over mux1 to the power an plus muz over muz1 to the power an. On cell F15, we are going to check the calculated value of interaction ratio. Defined name of the cell is check underscore 3. Formula is equals to if open bracket check underscore 1 not equals to OK, comma blank quotation, comma if open bracket interaction less than or equals to 1, comma OK, comma check close all brackets. Simple meaning of the formula. Again, in the formula structure, first portion is same as usual. If check 1 is not OK, the cell stays blank. Second portion of the formula says, if the value of interaction ratio is less than or equals to 1, then display OK, otherwise display check. Now we are on the last line of the design of short column as per IS 456, no charts needed, in Excel. Finally, we have to develop a final statement on our design calculation. To do this, we have to consider the merged cells from A10 to F10. The formula for the final statement contains 5 parts. Formula is: Part 1, equals to, if, open bracket, check underscore 1 equals to not applicable, comma, blank quotation, comma, if, open bracket, or, open bracket, p, less than 0.8, comma, p, greater than 4, close bracket, comma, check the percentage of steel provided, comma. Part 2, if, open bracket, n, open bracket, check underscore 2 not equals to OK, comma, check underscore 3 equals to OK, close bracket, comma, check uniaxial capacity, comma. Part 3, if, open bracket, n, open bracket, check underscore 2 equals to OK, comma, check underscore 3 not equals to OK, close bracket, comma, check biaxial interaction, comma. Part 4, if, open bracket, n, open bracket, check underscore 2 not equals to OK, comma, check underscore 3 not equals to OK, close bracket, comma, check both uniaxial capacity and biaxial interaction, comma. Part 5, if, open bracket, n, open bracket, check underscore 2 equals to OK, comma, check underscore 3 equals to OK, close bracket, comma, design is OK, close all brackets. Simple meaning of the formula. Again, in the formula structure, first portion is same as usual. If check 1 is not OK, the cell stays blank. Second portion of the formula says, if check 2 not equals to OK, and check 3 equals to OK, then check uniaxial capacity will be displayed. Third portion, if check 2 equals to OK, and check 3 not equals to OK, displayed statement will be check biaxial interaction. Fourth portion, if check 2 not equals to OK, and check 3 not equals to OK, displayed statement will be check both uniaxial capacity and biaxial interaction. Fifth portion, if check 2 equals to OK, and check 3 equals to OK, displayed statement will be design is O.K. So we can say, the function of this display is not only restricted within OK or check. It will also guide us for the particular points that we have to take care of. So, here we are finishing our PowerPoint presentation, but this is not the finishing point of this video. To conclude this video, now I am switching over to the original Excel sheet, from impression of the Excel sheet. We are now looking at the actual Excel spreadsheet. On this sheet, we will perform tests for a short and tied column, using SP-16, without the help of charts. At present, all cell values are blank. From the PowerPoint presentation, we already know this spreadsheet has 2 sheets. Sheet 1 is for analysis and calculation of the column. Sheet 2 is for loads and load cases of the column. First, let me remind you of the design parameters. We are seeing FCK equals 25 Newton per square millimeter. Fy equals 415 Newton per square millimeter. Clear cover equals 40 millimeters. Bar diameter 12 millimeters. Number of bars 12 numbers. Column depth in X direction 325 millimeters. Column depth in Z direction 200 millimeters. Unsupported height of the column 3.0 meters. Number 1. I will now change FCK from 25 to 15. We see that the cell is filled with yellow. Next, I change the value from 15 to 20. Again, the cell turns yellow. As per IS 456, 2000, we cannot use concrete grade less than 25 for new construction. Grades 15 and 20 are used only in retrofitting of old structures. Now, I will return to grade 25 concrete. Number 2. I am changing Fy from 415 to 250. We see the cell turn yellow. Once again, as per IS 456, 2000, we cannot use steel grade less than 415 for new construction. Grade 250 steel is only used for retrofitting old structures. Now, I will return to grade 415 steel. Number 3. The clear cover is shown as 40 millimeters, and bar diameter as 12 millimeters. First, I change the clear cover from 40 to 20 millimeters. Then I change the bar diameter from 12 to 16 millimeters. As a result, the clear cover cell turns yellow. As per IS 456, 2000, we cannot use clear cover less than 40 millimeters when bar diameter is greater than 12 millimeters. In practice, we generally use 40 millimeters for all bar diameters. Now, I will return to bar diameter 12 from 16 millimeter. And I will also return clear cover 20 to 40 millimeters. Now I am switching to sheet 2. In this sheet, there are two tables. Table 1 is titled Loads and Checking Column Capacity, 01. This table shows the loads and load cases for the column. These values come from the STAAD Pro V8i output of a column at foundation level of A, G, +4 building. Column A under the heading Load plus ABS moments is blank. Column F under the heading Check is also blank. This is because, at present, our column is not a short column. We also see another table titled Selected Load Case and Loads, 02. Here also, the columns for load case, Fy in kilonewton, Mx in kilonewton meter, and Mz in kilonewton meter are blank. For the same reason. Now I return to sheet 1. I will change the column dimensions. Both D and B are 250 millimeters. Now the column is a short column. Check 1 shows OK, which means we can proceed with design calculation. Beside uniaxial load capacities, check 2 is showing check. Interaction ratio is displayed as 2.930. It should be less than or equal to 1. Hence, check 3 is also showing check. The final statement is: check both uniaxial capacity and biaxial interaction, and also uniaxial load capacity. That means our column is in absolute danger. There is no way to escape. We have to save the column. Before saving the column, let us look at the top right corner of the sheet. Under Selected Column Loads, we see Axial load Pu equals 1147 kN. Moment about X, MUX equals 68 kN. Moment about Z, MUZ equals -6 kN. Now the question is, where did these loads come from? After watching the PowerPoint presentation, I think this is not a secret. This is an open secret. Now, I switch over to sheet 2. In the table loads and checking column capacity 01, the row of load case 209 is filled green. But its check cell is filled yellow. It is as if Excel is saying, I have found the maximum load case and loads for your column, but your column is not fit for these loads. Please review your design parameters. Looking further in the check column, we see that load cases 201, 202, 204, 206, 208, 210, and 212 are okay. This is an additional piece of information. Now, focus on the table selected load case and loads, 02. The selected load case is 209. Axial load Fy equals 1147 kN. Mx equals 68 kN. Mz equals -6 kN. We already saw these values on sheet 1. Now, I return to sheet 1, to make our column stand on its own feet. At present, column dimensions are D equals 250 mm. B equals 250 mm. Unsupported length equals 3 meters. First, I change D from 250 to 300 mm. Still, the design is not okay. Now, I change D from 300 to 325 mm. Now the design is okay. Now, let us see some boundary conditions for design. Number 1. The percentage of steel provided is 1.67%. I change the number of bars from 12 to 4. Now, the percentage of steel becomes 0.56%. As per IS code, the minimum percentage of steel should be 0.8%. That is why the design status shows, check the percentage of steel provided. Next, I change the number of bars back from 4 to 12. I also change the diameter of bars from 12 to 20 mm. Now, the percentage of steel becomes 4.64%. As per IS code, the maximum percentage of steel should not be more than 4%. That is why again, the design status shows, check the percentage of steel provided. Now, I will return to bar diameter from 20 to 12 mm. Finally, let us test the column slenderness ratio. I change the unsupported height of the column from 3 meters to 3.10 meters. Now we see a warning, long column. Then, I change the width of the column from 250 to 260 millimeters. Again, it becomes a short column, and the design is okay. Now, I will return to the unsupported height of the column from 3.1 meters to 3.0 meters. And width of the column from 260 to 250 millimeters. To control the slenderness ratio, we need to increase the minimum lateral dimension of the column. Once again, I return to sheet number 2. Now, take a look at the updated table loads and checking column capacity, 01. You can see that all the cells under the column check are now marked as OK. That means our column is safe for the load cases from 201 to 213. So, we really have nothing to worry about, our column's health is in good shape. In this way we can design our square and rectangular column. My next video will be on the design of short and tied columns, based on stress block parameters. The advantage of this method is that, it simplifies the design process, makes calculations faster, gives a more accurate estimation of strength, and ensures compliance with IS code provisions. Believe me, I could go on, and reveal many more secrets from this dashboard. But, considering the price of your time, I am stopping here. I hope this presentation has been useful, and maybe even a little enjoyable. If you liked it, please hit the like button, share it with your friends, and subscribe to the channel, so our column designs can always stand on their own feet. See you in the next video. Thank you.